I'm here for just 1 month for visiting Giovanni. I met Giovanni Parmigiani in Padova for a summer school about replicability. So we are doing a project together about statistical methods in replicability. Yeah, this is the reason why I'm here. And actually, this is my last week here. A little bit sad, but that's it. But today I'm not speaking about replicability, but about another topic that is my main research area, that is multiverse analysis applied to meta-analysis. We will speak a little bit about exploratory data, of course, analysis, so methods to explore the multiverse, but also about inference. That is a topic that is very important nowadays. So this is a little bit the outline. So I will give you a very short introduction about meta-analysis and multiverse analysis. Probably you know a lot about this. Then I have an example with some R code with specification to show you the actual implementation of the method, some exploring exploratory tools, a little bit of inference with two methods that are very popular now, the specification curve and the PIMA approach. We will see all these aspects later. So my presentation will be like 1 hour, a little bit more. So we can go straight and we have time for questions. Also during, it's not a problem. You just stop me and I will try to clarify the point. But if you still need a break, we can do a break even in the middle. So just tell me, it's not a problem. Yeah, so I'm a clinical psychologist, actually. I work in psychometrics and I did a PhD in experimental psychology. So I study a lot of statistics. My supervisor are statisticians, but I'm more on the, let's say, application side and less on, I don't have a formal statistical training. So keep in mind this. So very briefly about meta-analysis, because this is the model that we are going to use, and is actually the most common model in meta-analysis, in applied meta-analysis, especially in psychology and neuroscience, but probably also in biomedical sciences. So we have the so-called random effect model. Okay, so each observed study is a function of an overall true effect, average effect. Then we have the study-specific effect, that is the random effect, and the sampling variability, so the sampling error of that specific study. We have a linear combination, and we have our observed effect in the literature. The random effects are usually assumed to be normally distributed with a normal distribution centered on 0, with a variance usually tau square. Tau is the so-called heterogeneity, so is the amount of differences in true effect size in a given research area. And then the errors are, again, normally distributed, where the sampling variability is study specific, because it's essentially a weighted linear regression in which each study has its own sampling variance. This is why meta-analysis is important, because we can weight the studies according to the sampling variability, so according to the procedure. And theta is essentially the true effect for that specific study, that again is the sum of the overall average effects and the study-specific deviation. So this is the simple model that we are going to use. So we are going to estimate essentially two parameters. One is the average effect, and the other one is the heterogeneity. Of course, as this heterogeneity parameter goes to 0, we simplify the model from a random effect model to a fixed effect model, where each study essentially is estimating the same true underlying parameter. And of course, we are just estimating the average effect, that is the true effect. So this is the model. If you have some question, please stop me, but it's a pretty standard random effect two-level model. Just to give you a practical example, you probably can relate this maybe to your research area, I don't know, but it's interesting also to know some of you that are doing meta-analysis. So in psychology and neuroscience, usually our meta-analysis have very small K, so number of studies is very small, like 30, even less. Of course, there are projects with hundreds of studies, but on average, we have 30 or even less studies. A lot of heterogeneity, because actually pooling studies in a given, for a given effect or in a given research area, even if we restrict the search, still there are a lot of methodological differences. So we have usually a very large heterogeneity. And also, and this is an important point, is that when you do a meta-analysis, even like the search of the studies, data structures, the model and whatever, you have a lot of flexibility. So you can choose to include or exclude something. There is no like a standard pipeline. This is the point. So we have a lot of flexibility, and this creates, again, more heterogeneity in our results. And this is, of course, a problem. This is a distribution of heterogeneity parameters across meta-analysis in psychology. It's a project in which authors collected all the meta-analysis in a very famous journal and estimated the distribution that can be considered also as a prior distribution for the heterogeneity. So as you can see, the median heterogeneity in psychology and neuroscience is 0.2. You can interpret it as a standardized scale. So 0.2 in a standardized measure, so means that 0.2 standard deviations. Okay, is a standardized effect size, basically. And combining this information with the fact that, again, in psychology and neuroscience, the average effect using standardized measures is around 0.3, 0.5. We have a pretty wide prediction interval on the effects that we are expecting in a given research area. And this means that we have a lot of uncertainty in the final results, probably due to methodological differences. The effects are complicated. There are a lot of different ways of studying these effects. So this creates a lot of heterogeneity, but we have a lot of uncertainty. This is the point. To give you like an example, given that we are going to use simulated data, I think that is really always useful to simulate your data. This is an example on how to simulate a very simple meta-analysis with pre-post scores. So imagine that we have a treatment and we have the pre-scores and the post-scores, okay? And we want to simulate a bunch of studies using this kind of setup. So for a single study, we can imagine that our effect size can be formalized like this. So we have the average post minus average pre scores divided by some kind of standard deviation that we can, for example, pool the pre and the post or whatever. But the important point is that this is a standardized measure of effect size in standard deviation units, essentially. And of course, to calculate the sampling variability of this quantity to actually run the meta-analysis, we need to use, there are different formulas. This is one option. And this is the way to quantify how imprecise is the estimation of this parameter. And the crucial part is that given that we have a pre-post scores, we have the correlation between pre and post. We have to take into account the correlation to calculate the sampling variability. And we can do this very easily in R, for example. So you can set your parameters, 10 studies, 0.3, the true effect, heterogeneity, correlation between pre-post. We can assume that the correlation is the same in each study. We have the full correlation matrix. We can also calculate, simulate some some sample sizes across the case studies. We simulated through random effect. You see that I have the normal distribution here. So these are the true effects for each study. And we just iterate to all our parameters, and we will end up having essentially our data frame with 10 studies that are actually pretty realistic, right? We have the correlation, we have the variability, and so on. And again, if you are familiar with R, you know that there is the so-called metaphor package that can run meta-analysis in R. And in this case, you have your meta-analysis on the 10 studies. Just an example on how to simulate this very simple meta-analysis. So parameters in this very simple model are usually estimated with the restricted maximum likelihood approach. So especially the variance is estimated maximizing the log likelihood. This is the log likelihood for the simple meta-analysis. So with no predictor, just the average effect. And in terms of inference, and this is important for the multiverse part, usually this is done also here. So you have the estimated effect, standard error, and the test statistics and the p-value. This is computed using a wall test. So estimated parameter divided by the standard error, and we can compare this to a standard normal distribution or a t-distribution or whatever, and we have a parametric wall test. Another way of like doing inference with this type of meta-analysis is by using permutations. I don't know if you are familiar with permutations, but they are really nice because they're really robust to model misspecification. And this is nice, especially if we are not sure which is the correct model. But this is the very simple idea. This is important because we are going to use permutations in the multiverse analysis. So basically, we have the vector of the observed effect, that is essentially this vector here. We have our effects that we calculated from the studies, assuming that I use this. So I have the vector of y's. And what I do, I simply generate a random vector of -1 and 1, okay? I multiply this vector by the -1 and 1 vector. So essentially, I'm flipping the sign of the observed effect, okay? I rerun the meta-analysis, I extract the test statistics, and I repeat this for a very large number of times, let's say 500, 1,000, or even more. If the number of studies is small, I can do all the permutations. So there is a fixed number of permutations, but usually a large number is enough. And then I will end up having a vector of permuted test statistics under the null hypothesis, because flipping the sign, I force the null hypothesis to be true. Okay, this is the point. And then I simply can calculate a p-value comparing the permuted test statistics with the observed test statistics. And in this way, I can calculate a p-value without assuming normality and whatever. And this is a standard p-value using permutations. It's a one sample test, so we are just flipping the sign. But if you have two groups, for example, you have to flip the labels of the group assignment, and you can end up having the same approach. Meta-analysis using permutations. You can do something like this. Again, I did a very simple implementation, but usually there are packages for doing this. But in this way, you can see the actual flow. So you have number of permutations. This is the observed statistics. That is basically this one here. The observed is always the first permutation, is the way of doing. And then you generate the vector from like 2, because the first one is the observed one, to the number of permutations. You generate the vector. You multiply the observed effect with a vector. You save the test statistics, and then you compute the p-value. In this case, we have the p-value using permutations. Or in metaphor, in R, there is just a function to run the permutations analysis. So the idea is that, okay, we have a nice model, the meta-analysis model, we can do inference and whatever. But the problem is that the quality of the result of a meta-analysis is always related to the quality of the studies that you are including in the meta-analysis. Whatever is your very fancy way of analyzing the data, it's always related to the input studies. Also, if there is a lot of heterogeneity that is not clearly like controlled or explained, the results of the meta-analysis are not really useful. And of course, the degrees of freedom, not in statistical terms, but in a way that the way you conduct the meta-analysis can lead to different results. So if you like choose a model over another, if you choose an effect size over another, can have an impact. And in fact, with meta-analysis, you have a lot of degrees of freedom. You can exclude or include a study. You can exclude or include an outlier. You can use an equal or fixed effect model or a random effect model. You can choose some values. If there are missing values that you need to impute the values, and so other degrees of freedom, okay? And this is the essential part of a multiverse analysis. So real-world analysis requires a lot of steps and a lot of arbitrary choices. Usually we report just one choice, but we are not aware of like the impact of other choices. And what about reporting all the plausible choices when we have a data set? So if we are unsure about which model to use, let's do both and see what happens. This is the point. An example. I told you that with the pre-post correlation for calculating the sampling variability, I have the equation here, you need the correlation between pre and post scores to calculate the sampling variability. The problem is that when you don't have access to raw data, so you have to like extract your information from published papers, the pre-post correlation is usually not reported. So it's an information that you need and you need to impute if you want to run the meta-analysis. And for example, this is the impact of the correlation on the sampling variability. You see that using very extreme values have a huge impact on the sampling variability. And this sampling variability here is used for each study in your meta-analysis. If like this information is missing, you have to impute for every study. And even with a very simple example, so fixed or random effect model, which value for the pre-post correlation, some outliers to remove, you will end up having a tree of possibilities in your analysis. And only some of them, for example, could bring, let's say, statistically significant results or whatever your criteria to say that the effect is there. Only some of them. Maybe you are lucky and you choose one of these scenarios and you will have a very nice result. Or maybe you choose one of the options that is not bringing you the like the significance from a statistical point of view. But the point is that when you do just one of them, you are not aware about all the other possibilities. Maybe in some cases it's not like making a huge difference, but in other cases can make a huge difference. So let's use a more realistic example to simulate what happened in a multiverse analysis. In this case, I'm using something that I'm familiar with, but you can adapt the same idea to whatever your research field. So assuming that I have a meta-analysis on pre-post scores on, for example, a treatment for depression, okay, or whatever you can think, a randomized control trial or whatever treatment in which we have pre and post. Given that depression is a very complex psychological construct, usually we have multiple measures of depression. Maybe we can have a physiological measure, we can have, I don't know, the cortisol level, we can have a questionnaire for depression. So we have multiple measures for depression before and after the treatment. And we can essentially have a situation in which the study, so the paper, we have multiple papers, and each paper reports one or more outcomes of depression, maybe not all the outcomes, some paper only physiological measures, other paper only questionnaires, and so on. And but each paper reports a pre-post design. So we can have a situation like this. So the paper multiple times, first, second, and third outcome, the sample size, the pre-post effect, and the sampling variability. A pretty common like meta-analysis data set, okay? This is like an example of like the simulation. There is no the code because it's very long and probably not the best way to do it, but we can discuss if you are interested. But the idea is that given that we have three measures, so not just one, and the three measures are correlated because they are measured on the same pool of subjects, both the errors and the random effect comes from a multivariate normal distribution centered on 0 as the like univariate version. And we have, for example, different heterogeneity for each true measure and different correlation between random effects, and also different sampling variability and the correlation because the measures are collected on the same pool of subjects. So we have a dependency also at the level of sampling error. And so you can just like simulate data like this, and we'll end up having this kind of data set. But also a real data set with this type of design will look very similar. Okay, so the point is that usually this kind of data set can be simplified, essentially collapsing the measures within the same paper. Sometimes this can be like done from a statistical point of view, it's simply like combining the effect size, taking into account the correlation. And usually, if it's safe to do it, it means that the three measures like are related to the same underlying latent variable. Otherwise, you want to keep it separate. But in this case, let's assume that it's safe to combine the measure within each paper. So we will end up having a standard two-level model without having multiple effects within each paper. But this creates a situation in which we need to know this value, right? Because we need to combine the correlated measures. So we need to impute another correlation to doing like the aggregation part. And this is another degrees of freedom. Yeah.
Do you have to assume that all the measures are on the same scale? Like for instance, they all have to be from 0 to 100 or something? Or is that not really necessary?
Actually, when you compute like the effect size, this can be considered as standardized. So you are like pulling the pre and post standard deviation here. So when you do this,
it's more just like let's say for you have 3 different measures of depression.
Yeah.
That all 3 of them have to be, I'm assuming, on a similar scale to, or do you do the standardization of all those?
Yeah, you do the standardization before aggregating, and then you have essentially 3 measures on the same standardized scale.
I see.
Yeah. And so also it's safe to combine because they are all on the same scale. We can discuss if it's appropriate or not, but they like using this transformation, we are putting everything on the same scale. Yeah. So let's like do a very simple multiverse, because usually this can be like hundreds or thousands of different analyses. But assuming that I want to choose 4 values for the pre-post correlation to impute to calculate the effect size. Then for correlation, this one. So I need to impute this to aggregate. So I have other 4 correlation, can be 5, 10, whatever, just 4 to have a more manageable example. And then I want to run the fixed and the random effects model. So I don't know which is the best one, so I want to run both. Okay. I do all the combination like a factorial design, and I will end up having 32 different analyses on the same data set. Again, this is a very small number, usually can be hundreds or thousands, but in this case, the idea is the same. I do all the combinations, so I will have a meta-analysis with correlation 1, fixed, correlation 2, all the combination. So imagine that I do this, I do the 32 meta-analysis. So essentially, I no longer have a single result, but I have 32 results. Now we can start exploring a little bit. So I will present you some kind of plots that can be useful, because we are increasing the level of complexity of our analysis. Because imagine to have 100 results, it's not easy to report it. So the first option is to make things like more interpretable. In this case, I transform the p-value of the results into z-score. This is a very common transformation. It's useful because also plotting, the plots are nicer, but also if you are more familiar with z-score, it's better to interpret p-value in this case. So a very small p-value will be an higher z-score. Okay, I'm using just the cumulative function of the standard normal distribution. And if we assume a 0.05 as alpha value, the critical p-value will be 1.96, roughly 2. Okay, and lower, like higher p-value will be lower z-score. This is the transformation. So this is a first plot. So each dot is one meta-analysis of the 32. On the x-axis, we have the estimated effect, so the estimated average effect from each meta-analysis. And on the y-axis, we have the corresponding p-value z-transform. So as you can see, in this simulated example, again, these are simulated data, so they are created with like teaching in mind, but an actual meta-analysis, multiverse analysis can be something like this. So as you can see, there is a lot of variability in the estimated effect, right? So sometimes in some condition, the effect is very low, if not close to 0. In other condition is higher. And also in some meta-analysis, the result is significant. And in other meta-analysis, the result is not significant. This creates a huge problem because actually, if you choose to report, for example, this one, you will end up having different conclusion than reporting this one, right? This is the point. And it's a problem because in like common scenarios, I would have choose like one single value, so one of this one, without being aware of this complexity. Another possibility is that we have essentially a factorial design. So we can consider the multiverse analysis as a factorial experiment. In this case, it's not always a factorial design. So we can see, for example, the marginal distributions of the effect size, the estimated effect, according to my factors. So here I'm plotting like the distribution of the 32, in this case, like half for each model. So the 32 models for the fixed effect and the random effect model. So this is fixed effect model, this is random effect model. And as you can see, there is not a huge influence of the type of model that you choose, right? The two distributions are pretty similar. And if we do the same for the correlation between multiple outcomes, so the correlation that we use to aggregate the effects, you see that, for example, there is a lot of variability according to the correlation. So systematically, if I choose an higher correlation, I will end up having higher estimated effect. And actually, in this case, probably the correlation between outcomes is explaining most of the variance of our multiverse, but in other cases can be more complicated. But given that we have a factorial design, we can also do the interactions if we have a lot of scenarios. So maybe interacting the model with the correlation, and we can see that, for example, only if we use an high correlation and a random effect model, we'll end up having high estimated effect. But this is just exploring. Another possibility, this is a little bit more complicated, but very like useful. In this plot that is called specification curve plot, in like the top panel, we have essentially the 32 meta-analyses, the 32 estimated effects sorted from the lowest to the highest, and the confidence interval of the estimation. And on the bottom panel, we have all the conditions. So this is the correlation between pre-post scores. This is the correlation between outcomes and the two methods, the two analysis model. And essentially, you can read this plot like vertically. You can slice vertically. And for example, these meta-analysis has this value when there is the black tile for the pre-post correlation, this value for the correlation between outcomes, and is unequal effects fixed effect model, right? So you can read it like vertically. But the point is that we are lucky here because it's a very simple example. You can clearly see that there is a clustering of estimated effect according to the outcome, correlation between outcomes. That this is the same result as here, basically. You see that systematically, meta-analysis that use this value for the pre-post correlation, for the correlation between outcomes have like higher effect and significant effect. And maybe here the situation is more intermixed. So means that the model is not actually making a huge difference in this analysis, right? Again, this is easy to like read here because we have a limited number of studies. We have like 1,000 meta-analysis. Is not so easy, especially if there is no clear pattern like this. But in any case, it's a nice way of representing the results. Okay, so again, just exploring. So we increase the complexity a lot. But the point is that, so what now? What we should do if we have this kind of situation? So we trust we trusted our colleagues, say, okay, you have to run a multiverse analysis, but now you have this complex situation that is significant sometimes, not significant in other times. It's complicated. So the point is that we need some method to pool the results and still like have a final conclusion, possibly an inferentially valid final conclusion from the multiverse analysis. What is the problem? If you think about these scenarios, the problem is that we are testing the same hypothesis multiple times. So we have for sure a problem of multiple comparisons, a problem of multiple tests. There is for sure an inflation of the type 1 error here, right? Because we are testing the same model multiple times with the same data set and with the same hypothesis, essentially. And this creates a huge problem because these p-values that I'm like presenting here, I'm saying sometimes significant, sometimes not. These are raw p-values. I'm not taking into account the fact that there is a inflation of the type 1 error. And so even look at the multiverse from an exploratory point of view, plotting the p-values and so on, is problematic because these are raw p-values, and with thousands of tests, we will end up having a huge inflation of type 1 error. So we need a method that, yeah, like combine the results, but also it's valid from an inferential point of view, especially in terms of type 1 error control. The first approach is the specification curve. So the plot that I show you is the graphical version, but the actual specification curve is an inferential method. This is the idea. It's a paper published recently. The idea is that, I go back to the plot. So let's imagine to have, this is the observed specification curve. Okay, so the specification curve that you can plot from the one multiverse analysis, essentially what you presented, so the 32 scenarios. So let's imagine to apply the permutation approach that I introduced at the beginning. So permuting the, do a permutation test for each of the 32 meta-analyses, right? Not just one, but because we have 32 meta-analyses now. And then recomputing the specification curve for every permutation. So we will end up having not one of these, but B, if B is the number of permutation, B specification curves, essentially, under the null hypothesis. And this is the point. So we define the specification, the M specification. In this case, we have 32, right? We permute the data, we refit the model, and then we can calculate global test statistics, for example, the median of all the 32, or the mean, or the sum, whatever. And then we will have essentially the null distribution of the median across the multiverse for B permutation. And we can just compute our p-value across all the multiverse. This is, it's very long. We can discuss it maybe later, but it's an example of how to do it. Essentially, I rerun the meta-analysis for each of the 32 with the appropriate method, in one case, one correlation, and so on, taking into account all the multiverse. But then the point is that I run the meta-analysis permuting the test statistics. So this is an example of what can happen. So, these are like 100 permutations, so 100 specification curves under the null hypothesis. And the red one is our observed specification curve. So essentially this one here. So I simply can compare the actual specification curve with the null distribution. And for example, here I'm computing the median of each specification curve, and then I calculate the p-value as the beginning. So this p-value that is, in this case, it's a very low number of permutations, so it's basically 0. This means that in each permutation, systematically, the observed one is higher than the permuted one. And this means that, at least in this example, there is a strong evidence for that my specification curve is not like coming from the null distribution. This is the point. The problem is that with the specification curve is that it's very computational expensive because think about it. In this case, we have 32 meta-analyses that we have to run again for a large number of times. So it's like if you have 1,000 scenarios and you want to do 1,000 permutation, it's crazy. It's like you can do it, of course, but will be very computationally expensive. But the most important part is that if you are a little bit familiar with p-values adjustment, the way that we calculate this p-value and the test, is called weak control of type 1 error rate, family-wise error rate, because we have only a global null hypothesis. We can just say that there is at least one of the 32 scenarios in which the effect is different from 0, okay? And this is problematic because we have just a p-value overall, but we cannot look at single analyses and to say what is going on in a very specific analysis out of the 32 scenarios that we have. So it only provides weak control of type 1 error. If we want to provide stronger control of type 1 error, we need to adjust the single p-values. But the problem is that usually methods for adjusting p-values, like the Bonferroni, the Olm, or whatever, are very conservative because they consider that the p-values are orthogonal, and so they will provide the strongest correction with a very low statistical power. And this is the method that tries to solve this problem. This is called PIMA, so post-selection inference in multiverse analysis. Has been developed by my colleagues in Padova, and with the collaboration also from other researchers. But the idea is that we want to provide essentially strong and weak control of type 1 error. So we want the global null hypothesis, but also we want to comment each single scenario. We want a method that is very flexible. And in fact, the original method published here, it works with whatever GLM that you can think about. So whatever the link function, whatever the model, confounders or not, whatever model that is in the GLM family. And it's based on the so-called sign flipping score test. That is a test based on the likelihood function, essentially. And the most interesting part that is better than the specification curve is that provides adjusted p-values using the so-called max-t method. It's not important the actual method because there are also other ones, but the important point is that it's used an adjusting procedure that takes into account the correlation between the 32, in this case, scenarios, providing a less conservative test, but still providing a strong control of the family-wise error rate. So very quickly, and the actual implementation is really complicated, at least for me. The point is that we can write the score function is essentially the derivative of the log likelihood with respect to the parameter of interest. And we can write that each observation contribute to the sum of the scores, okay? And we can use these statistics with the same permutation approach that I showed you at the beginning. So we can just flip the sign of the scores, okay? And in this case, we have a test that has a lot of nice properties that is robust, can be used for whatever GLM. But the actual interesting part for the meta-analysis is that the score function, so the contribution of each study to the score function, very simple, and is basically this one. So is the difference between the estimated effect and the average effect under the null hypothesis, that is assumed to be 0 in this case, so we have just this one, divided by the sum of the study-specific variance and the heterogeneity estimated under the null hypothesis, because we are permuting, so everything is estimated under the null hypothesis. For each study, we have these that we call scores, and we can just flip the sign of the score as we did at the beginning, and have like this test instead of the standard meta-analysis. So this is a little bit the workflow. So we start by case studies and M scenarios. So in this case, we have like case studies and 32 columns, so the 32 scenarios. We estimate the heterogeneity under the null hypothesis. There is a method to it, but it's just maximizing the log likelihood under the null hypothesis. We're calculating the scores, as I show you. Then we apply the permutation test, but now it's multivariate because we apply the same test for each scenario of the multiverse. So we'll end up having a B permutation by M matrix with all the permuted statistics and all the scenarios. And then we can just run a one sample permutation test, multivariate in this case, providing the overall p-value, but also adjusted p-value for each scenario. I will be brief here because it's not really crucial because there are other methods, but all methods to correct the p-values that are based on permutation provide these nice properties. So These are a bunch of tests, correlated tests. It's just a simulation from a multivariate normal distribution to show you what happens if you use a standard Bonferroni correction or a correction based on resampling, so based on permutation. What you see is that the Bonferroni that is not taking into account the correlation is assumed that all the tests are independent, essentially provide a very, very, very conservative test. So on the x-axis, we have the raw p-values, and on the y-axis, we have the corrected p-values. If there is no correction, of course, the p-values are on the diagonal. But as we go like here on the top left corner, of course, there is a very strong correction. And as you can see, the sampling method, the max-t in this case, is very, very, very like conservative as the Bonferroni when we have a low correlation. But it's less conservative, still providing type 1 error control when the correlation is higher. And for sure, the correlation is high in multiverse analysis because you are testing the same data set. Even if you are changing a lot of stuff, still the data, like it's the same data set. So the correlation is for sure very high. Again, the implementation is simple. It's just calculating the scores. These are the scores, the observed scores, so the effect size, sampling variance, and the heterogeneity under the null hypothesis. And there is this flip package for doing the multivariate permutations. This is the global p-value. So the p-value where the null hypothesis is that there is at least one scenario in which the parameter is different from 0. But the nice part is that we can adjust the p-values. I think that this is the most interesting plot because on the x-axis, we have the raw p-values from the 32 scenarios, okay, that were the p-value that I presented you at the beginning with the exploratory part. And on a y-axis, there are the corrected p-value using this framework. And again, in z-value, so the like higher is lower, and here is the threshold for significance. And as you can see, there are some of the 32 scenarios that were like not significant before, and of course, they're not significant after the correction. Some of them, the red ones, were significant only before the correction, so they did not survive. But the blue ones, they are the most interesting one because they survived the correction. And among these blue ones, we can just pick the model that we want. We can just report the model that we want without inflating type 1 error. So if all these models are plausible, and this is a sort of assumption of a multiverse analysis, you cannot put garbage in a multiverse analysis, you can essentially pick one of the models that you prefer for whatever reason without inflating type 1 error. So the blue one, you can explore there. You can see, okay, this is better, this is, I don't know, without inflating type 1 error. This is the message. And we can like think about sort of legal p-hacking because we can just pick whatever without inflating type 1 error, without committing any type of questionable research practice. You can also combine the two, like the plot with the adjusted p-value, providing a more like informative picture in which you have the exploratory part, but the p-values are corrected with this entire framework. So it's for sure better. So like I'm like almost done. So the idea is that maybe we can improve the method assigning a sort of weight to each scenario because yeah, these 32 are plausible, but maybe they're not plausible at the same level. Some of them are more plausible for whatever reason, statistical reason or empirical reason, let's say, given that we know the field. So maybe like considering that the weight is the same is not the best option. So we can think a more like a prior probability of plausibility for that specific model. Some people are also questioning if like inference is useful in multiverse analysis because some people say that you can just explore. This is an option. We can discuss it. And if you have any comment or suggestion, I would be really happy. If you want, there are some packages for like doing whatever I did in the presentation. So there is a multiverse package that essentially creates the multiverse for you from all the specifications. there is the this package for running the specification cure and the joint test package that is the package developed by the authors of the paper, the PIMA paper for running the PIMA analysis. But we are still working on the final version of the package. Thank you.
You could let people know online to use the chat function, or maybe just.
Oh. If you have any question, I'm here, of course.
So like technically speaking, you could use that approach by so if it was like an outlier example, and you had like in like 20 different studies.
Yes.
You could maybe do 20 different scenarios where you leave one of those studies out and kind of run an analysis based on whether you include or not include. Okay, interesting.
Yeah, like removing studies or observation, because my work is implementing the method on meta-analysis, but the initial method is for standard studies in which your statistical unit, like people or animals or whatever. So you can, one of the way of creating specifications is to, for example, remove an observation. So yeah, this is an option, is implemented to work with, like, let's say, missing observations. Yes.
Do you often do, because in one of the examples that you discussed, or that the main example, there was like potentially multiple different measures of the same kind of outcome, like you said, for depression. Do you often have cause to do where like in a meta-analysis, you actually have multiple different sort of measures in there?
Is like
realistic. Like the example that you were like, did you actually run that kind of study in the past?
Yeah, mainly meta-analysis that like the majority of meta-analysis that I work on are like multivariate meta-analysis. So sometimes I aggregate the effects because maybe I want a simpler version of the model, but sometimes maybe also want to know, like, let's assume that we have 3 measures of depression, want to see if the effect is specific for one of the measures. So in this case, I have to run a model that taking into account the 3 measures and estimate an effect for each of the 3 measures. So there are both cases. The method can work also for multivariate models. So it will provide you, for example, 3 global p-value for the 3 outcomes, but it is like a little bit complicated to present, and also I didn't try myself yet the model, but we can do it.
I think it's very interesting because I guess without having seen this presentation, I would have expected you to have to do, totally separate, or there wouldn't have been a way to kind of combine those measures, but that's very interesting.
Yeah, of course, the problem is that you have to make some assumption to combine the measures, especially like in meta-analysis, because again, if the measures are correlated, you have to impute a correlation, or if you have the raw data, you have to like combine, taking into account the correlation. But most of the time, at least like in psychology, like now in the recent years, people are like providing raw data. But if you are doing a meta-analysis with studies like 10 or 20 years ago, at least in psychology, I don't know in other field, like raw data were not available. So you have to make some assumption most of the time. And
yeah, we, in one of my recent projects, we had to do a meta-analysis for like survival kind of outcomes. And there were some studies that were like 20 plus years old. It was painful like trying to get the information from those.
There is a huge like literature on not really meta-analysis from a statistical point of view, but to extract data from studies, convert the measures. If I have the t-statistics, can I have the odds ratio and the opposite? And yeah, it's another word.
Yeah, it was surprising how many didn't report, like especially those old papers didn't report the hazard ratio, but survival is kind of the main result.